Okay, so I'm going to start with this Joule-Thompson experiment. This is a chapter 2D, and then this is a section number 5. So this is a Joule-Thompson experiment, or they call it effect. The most important part that defines this Joule-Thompson experiment is this mu, and mu is defined as when you change your pressure, what is your temperature change that you want to know? And this experiment they are designed is under constant enthalpy. So this is an isenthalpic process, and how those design can come about, what are the experiment is too famous, I guess, for scientists. And if there's a name for this, it's a very kind of iconic experiment that is quite important. So this Joule-Thomson experiment is on the Q equals 0. We call it adiabatic. Okay? And then we can start to draw the syringes. And then there is essentially this porous plug. And then in the beginning, you are having this P1 and this P1, and there's no volume on the other side. And typically this is a P1 is high pressure, which is a compressed gas. Okay? And then you let this one go under adiabatic condition. What that means is no extra heat is applied. Just let's see what happens if I just compress the gas and let it release to the other side. So I guess a final easy picture for me to visualize is, okay, let's say you have nothing there, and then you kind of have an expanded volume on the other side, and that is a P2 to P2. So the P2 is lower than P1, and this is typically expansion experiment that you do. And I have given here, this is a typical situation where this side is in the initial, you have a compressed gas, and then let go, and the other one is expanding it. And my interest is, okay, I can have a high pressure to low pressure. What happened to the temperature of this gas? Is it going to go up or go down? And that's really the thing that they are interested in here. Okay? And then, but when you define this, and I'm going to work and essentially say, I'm going to prove Joule-Thomson process experiment is isenthalpic process. Okay, so I'm going to prove that this is an isenthalpic process, which is actually shown up here. And what I need to do is I need to define my system. So what is my system is, this is my system. I guess with a little bit of something, nothing there, but those are the system in both sides. So these are essentially gas in this side and gas in the other side is my system. This is my system. Okay, so that's my system before and after, which is this is essentially my gas of my interest. So that is my system. The system is changing its volume and so on. And then once again, there's no extra heat. You don't put any burners or heaters to maintain the temperature constant. You just see, essentially, without any help from the surrounding, see what happened to this temperature. And to make this calculation easy, I need to define my work. So for this volume change, the work is defined, and this one is, I'm going to say, pressure 1 is being experienced throughout. And then when they expand to the other side, they have to expand against the P2. So these are the sort of the very simplified diagram to show it to you. So then I am going to start with something that equation that looks familiar, delta U with work plus fuel. Right? So this is something that I can start with. And that's easy. There's no heat. So this process is defined by this work. But now the work for this Joule-Thompson experiment can be defined, I will say it as work 1, work 2. So work 1 is work on the left-hand side, work 2 in the other hand is the right-hand side. What do you think about the work? This system, when the pressure is being pushed, is it positive or negative? What do you think? You should have an expectation, right? This is a gas. They are receiving the pressure from the outside. This is essentially compression, right? They're essentially receiving the work from the outside. So you should already have an anticipation that this is a plus, and this is an expansion. So this is a negative. That's the other side. But keep that in mind. This is just something that always a double check for you to do. But now, let's just do as normally we usually do. Remember that work is external delta V. That's for the irreversible process, and this is let's say is a irreversible process against the constant pressure. This is, I guess, against or with the constant pressure, external pressure is constant. So I'm going to use the same thing, P1. But now the interesting part is, yeah, this is always a negative against, but what is your final volume? Always delta V means V final, V initial. So what is your final volume? 0, right? What is your initial volume? V1. So can you see that? This is actually becomes plus. Okay? So that should make sense to you without actually the equation or being careful about the equation sign. So this one by itself is defined as it is. And the second portion is minus P2. Your final volume is V2 minus 0. Right? Your initial volume was nothing. So this, just put a sign like this. So this one naturally comes to P1 V1 minus P2 V2. And this is not so bad because this one is, according to this is same as this work is same as delta U. And what is your U? Final is U2. This is only internal energy. The other side is nothing. And what is your initial? This is your internal energy in the beginning. So now, do you see that now, right? This one, this one, this one, this one. So it's pretty easy for you to say P1 V1 is U2 P2 V2. So then what naturally say, oh, H1 is same as H2. Essentially when Q is 0. Okay? So this is, I just proved that it is an isenthalpic process. Before and after, your enthalpy stays the same. So if you do the adiabatic expansion from compressed gas to expand to the other side, so by this kind of Joule-Thomson experiment, that's the part that I can happily run. Okay? So that's the one. And then what do? And then I have to put something that, what do you want to know? You want to know temperature change, right? And what do you kind of manipulate? You want to have a different pressure contrast. So this is what they say, okay, this is something that is defined, and just Joule-Thompson says, let's call it as a mu, and this is a Joule-Thompson experiment. Okay. Thinking back, and then let's talk about this meaning. And if I'm going to say if this is true, if this is a positive, and let's see what it means. And for this process shown up here, your initial pressure is higher than your final pressure, right? So in this kind of scenario of compressing the gas and expose it to the outside, what is a sign of your pressure change in this particular process? Is it? Your final pressure is lower than your initial pressure is. So this is a particularly more practical consideration is upon expansion of compression, compressed gas, right? Upon compress the gas and let it expand it out, your delta pressure change is negative. Your final pressure is lower than your initial pressure. So normal situation is, this is round T. This is something that I'm of my interest, and this is essentially negative term, right? And then I told you that if this is a positive, what this one has to be, that has to be negative, right? So what that means is, if this is a 1, delta T is negative. And so what this whole thing, I mean, this is not even a good looking equation. The good statement is compress gas release on the adiabatic condition. This is what Joule-Thompson experiment is about. And when mu is plus, you can have, this is what you've been looking for. You will have cooling. Cool? This is what's important. So the meaning of Joule-Thompson experiment, they can be positive, and this is what actually we have been looking for. If this is a positive, if you compress the gas like this, and then if you let it expand it, and then this compressed gas will be cooled down to a lower temperature. And so you cool it down, and then you will essentially collect this cooled gas, and compress again, and then adiabatic expansion, you can continue to cool the gases down. And this is a very important. Okay. And then I'm going to show you actual experimental diagram. And can you also make sense? If it is a compressed gas, the intermolecular distance is very close, right? And you let it expand, they're falling apart. Right? If this gas like each other, have attractive interaction, you force them to be apart, you are going to put some energy. You need an energy to, I guess, these loving partners to be apart each other, right? And you need the energy to put it in, but what happened? There's no energy from the outside. So what do? You just have to, I guess, bite the bullet. You have to do it by yourself, because lowering your kinetic energy or lowering the internal energy, that's the only source that you can use, right? So that's what happens. So therefore, the temperature is coming down. Right? So that implies that there is an attractive interaction. So the diagram that people draw, and I'm going to. This is a quite typical experiment people do. This is a pressure. This is a temperature. And that's a typical sort of the region where your mu is positive and mu is negative. And then I can say that this is a cooling. This is I guess the other one is heating. because probably not so interested in. Because I can heat the gas. You know, heating the gas is such an easy task, right? You can just heat it up, the gas. Well, how can I cool the gas? And then this is by simply expanding and then release the gas. You can get this cooled gas coming out. So those are the sort of the idea. So if you remember this, when you go pressure go higher and higher and higher, what's going to happen? There will eventually. I mean, this is an attractive interaction. I mean, in the beginning, the low pressure, they are miles apart. There's no interaction at all. And if you start to coming in, they will have an attractive interaction. But if you're splitting too much, like this scenario, they will have a repulsive interaction. Eventually, you are doomed here. At extremely high pressure, you will have a repulsive interaction, so there's no way. Okay? But within this pressure ranges, that is still typically in the 100 atm pressure. And I am going to draw this one more time now. I'll just throw, there are so many other examples. Each gas has a different kinds of cooling and heating criteria. And this is for the mu is positive here, mu is positive here. This is for the nitrogen gas, this is for the helium gas. So I just want to highlight this particular narrow window where you can cool the helium down. So you have to use a nitrogen to have a cooling effect so that you can maintain the temperature to be low enough, and then you can start to have this compressed gas release. You can further reduce the temperature to this. So the helium is really I think a lot of physicists in old days, they are interested in. It's just such a very well-defined gas, single monoatomic gas, almost no polarizability, so they want to study and then understand the property and make it more challenging to understand, and because they have a very low critical temperature.